In this video we're going to be talking about optimization, and this is going to be using derivatives and calculus in order to get us that optimized value. So what is optimization? That's when we are trying to maximize or minimize quantity A, whatever that might be, by changing or modifying quantity B. And in order to do this, in order to optimize these values and make these connections, we're going to follow 5 basic steps. So the first one is to find the relationship between these two things, A and B, whatever they might be. Oftentimes they're connected through what's called a constraint or some other value that's imposed on these things that kind of keeps it limited. And you'll see what I mean when we go through a couple examples. The second step we're going to do is we're going to use the first derivative to find or identify any minimum or maximum values. Then we're going to use the first or second derivative test to confirm whether these are minimum or maximum values. And then we're going to check any endpoints of domain or possible for possible minimums or maximums. And we can even look for asymptotes depending on the type of function. Now, to be honest, this particular point is kind of specific to when you are given a restricted domain. This isn't something that you're generally going to do for every single optimization problem, but it is a good one to include in there as you are going through the process. And then finally, the fifth step is to basically answer the question. All right, so let's get started. Here's our example. We are going to find the dimensions of an open box with a square base and a surface area of 192 centimeters squared. And what we want to find is the dimensions that maximize the volume of this box. Okay, so let's assume we've got this box here and we've got these three sides. So the base is a square, so the dimensions are x and x because they're the same length. And then we've got the height of the box, which we'll call h. Okay, so our volume is length times width times height, so that's x times h, or x squared h. Surface area for a box or a prism is basically adding up the area of all the different sides. So since we have an open box, that means we don't have a top on it. So we normally would have the top and the bottom would be the same dimensions, but since we don't have a top, we just have the one bottom, which is going to be x squared. And then the four sides that go around, they all have the same dimension of x times h, so we're going to have 4 of those. And we also know that the surface area has a total measurement of 192 centimeters squared, so we can just pop that right back into this equation as well. And basically, this is number 1 from our steps over on the left. This is finding the relationship between these two things. So we are looking at the volume. That's what we're trying to ultimately maximize or minimize, in this case maximize. And we're trying to find the connection between those. Well, it's going to be between these two formulas because these two things both use the side lengths, the base x and x and the height. So both the surface area and the volume use these two connected values, and so we can combine all of these to find the volume. Now, so we normally want to try to maybe isolate one of our variables in order to get everything kind of dumped into the volume formula, since that's what we're ultimately focusing on. So we could try to isolate x, but I think it'll be easier to do the h because there's only one h in here. So we're just going to start some rearranging. So we're going to subtract x squared to the other side. We're going to divide both sides by 4x, and we're left with h equaling 192 minus x squared over 4x. Now, what is the point of this? This then can be dropped into the volume formula for the height. So now, when we simplify this out, we've got ourselves, or we're working towards getting ourselves a nice volume formula with only a single variable. So if we continue breaking this down, kind of getting that denominator sorted out, we have our volume equaling 48x minus 1/4 x cubed. Okay, so now we need to look at the derivative of this because we want to find the minimum or maximum. And the derivative is 48 minus 3/4 x squared. Hopefully you were able to do that already or recognize that. And we are going to set this thing equal to 0 because we want to know where the minimums or maximums of the function are because the minimum because we're looking for the maximum. So we set it equal to 0 and we solve for x. So we move the 40 or get the constant on the one side. So 3/4 x squared equals 48. Multiply both sides by 4/3 to get that x squared by itself, and that simplifies to 64. And of course, take the square root of that, and we get x is equal to plus or minus 8. This essentially is step 2. So now we found the derivative to identify any possible minimum or maximum values. And that's going to happen when our dimension for our base is 8. So our x value could be positive 8 or a negative 8. So now we're going to move on to number 3. And that's going to be using the first or second derivative test to confirm the minimum or maximum value. So we'll take the second derivative, and the reason I'm taking the second derivative is because I know that since I have a quadratic for my first derivative, my second derivative is going to be a linear equation, which means it's either going to be just a positive or a negative linear equation. So it makes the looking for the minimums and maximums a lot easier than trying to plug things into the first derivative test using our first derivative. Okay, so let's start with positive 8 because if we plug a positive in here, we know we're going to end up with a negative value. So since it's going to be a negative value, that means it's going to be concave down, which means that 8 is going to be a maximum value. Now, we could have, so we're looking at 8. So we could have put negative 8 in there to confirm as well, but there's two things that are going on. First, if we look at the second derivative, we see that it's a negative function, so that will give us a positive function, which would then give us a minimum value. Second, if we look at the context of the problem, we can't really have a negative dimension. So that's another clue on why I chose positive 8 to begin with. Okay, so we've got our maximum value. We know that 8's our maximum, so now let's find what the actual height is. Because we don't really need to check our endpoints because we don't have them, so we don't need to really work with that at all. So we're going to go on to start working towards number 5 and answering the question. So let's start by finding the height. So we're going to plug in 8 into our height equation. We're going to do some simplifying, and we're going to get our height is equal to 4. So now, as we answer our question, what are the dimensions of this open box with the square base? Well, they are going to be 8 centimeters by 8 centimeters by 4 centimeters. So that's the solution to this. We've answered the question. Now I want to go through one more example so you can see a different type of problem. This is probably one of the most common types of problems, comparing volume and surface area. The other seemingly most common type of problem is when we have something that looks like this. A rectangular plot of land is enclosed by 180 meters of fence on 3 sides. The 4th side is along a stone fence, so we want to find the dimensions to maximize the area and actually find the area as well. So let's draw this out. So we've got the widths are going to be the same and the length is going to be a different dimension. Now again, this is the second most common. This is kind of comparing perimeters to area. So volume to surface area, perimeters to area, these two types of problems are generally the most common, but you can optimize lots of different things. Okay, so as we proceed, our area is going to be length times width. That's ultimately what we're trying to optimize. And our perimeter is length times 2 widths, which you can see from the picture there. So since we know what the perimeter is, we know that's going to be 180 plus length times 2w. And this here is our first step. So we've now connected these two things. We realize we're optimizing the area, and we're connected between the same length and width for the perimeter and the area. Now you could isolate either the length or the width. In this case, it looks to be the easiest to isolate the length, so I'm going to get that by itself by subtracting 2w from both sides. Okay, so then we can take the area and put in 180 minus 2w, which is just substituting the length in from the perimeter function, and we're going to multiply that by w. We'll do some simplifying, and now we can start working towards step 2. And we're going to take the derivative and try and find the minimum and maximum values. So the derivative of the area with respect to the width is 180 minus 4w. We're going to set that equal to 0, get 4w on the other side of the equation, divide by 4, and our width is 45. Okay, so number 3, use the first or second derivative test to confirm the minimum and maximum. Now, my first derivative is a linear equation, so I can just stick with that. So I'm going to make a number line. I've got my 45 here, and I'm going to take a value smaller than 45. I'm going to substitute it into w, and when I do that, let's say I put in 0, I'm going to be left with a positive value. 180 is a positive value, obviously. Take something bigger than 45, so I'll take a nice big number, let's say 100. And we put that into our derivative function, and we get negative 400 and 180. So we're going to obviously be left with more negatives than positives. So our slope of the equation using the first derivative test, because again, that's the easiest one to use here. We didn't have to go to the second derivative. Using this, we see that the slope is going from a positive to a negative, which means that 45 is a maximum value. Okay, so we found that maximum value. Now, we don't need to check any endpoints because, again, we don't have any restrictions on our domain. So now we're going to work on answering the question, number 5. So we take our length and we put the 45 in there for our width, and we end up with a value of 180 minus 90, which is a length of 90. So the first thing says find the dimensions. So the dimensions of this rectangular plot of land is going to be 45 meters by 90 meters. And the second thing we're supposed to do is maximize the area, or find that actual area. So we just take 45 by 90 and we get 4,050 meters squared. So that is how to use optimization for a couple different types of problems. Hopefully this is helpful, and I will talk to you in the next video.